testing this new Meg System 5, and as you can see here, the scope is showing, well, it just sped up on me, but you can see these pulses, and they're above the third mark. They're about like 35 volts above zero line, because we're at 10 volts per division, and we're at the 0.5 millisecond frame rate. And basically we're measuring between the water here and the positive coming in off this Bendini motor after it goes through this little electrolytic capacitor. And if I can focus in on that, as you can see, we got our ground connected to this water here, so we're measuring the ground relative to the water. And then it's kind of cool is I can touch the water when it's off, and it increases the amplitude. And then if I try to measure the voltage across these leads on the primary coil, it basically measures nothing on the multimeter, but on the scope it shows up, you know, like 35 volts or so. But I've gotten it to go off the screen here without this capacitor sipping off of it. Basically we're dealing with some displacement current here. We're powering these LEDs. If I turn off this light, off of these secondaries here, and essentially if I were to take this wire here and take it off, you can see that light up. So it's kind of like either it lights up this LED or it lights up these ones. Kind of interesting. They're both wired in parallel to the same thing, but it won't light up the same depending on how far away it is. If I turn this off, now you don't see much of anything until I zoom in the volts per division. We're at 50 millivolts, 20 millivolts per division, and you see all this noise. We're at 0.5 millisecond frame rate, 20 volts per division, that's 50. So it's like 100 millivolt bandwidth. With other configurations, I get it up larger with just background noise, but yeah, this is just showing through the water, the background noise. Get it going again. You can see scope, 50 millivolts, 0.1, 0.2. So you can see there's a lot of negative spikes, but there's also some positive spikes. So that's 5 volts per division, and that's 10 volts per division. So it kind of falls back in line with this impulse state. And then, hello YouTube, doing another experiment. What we're measuring here with the scope is the DC output on this full bridge rectifier, and the AC side is on the positive side is the negative terminal, the return path of this coil, and I have blocking diodes there for the Bendini motor, even though it's still seeing some there, as you can see. And then basically on the ground side, you can see I'm grounding it into a cup of water. And then so you can see my output here, it started at 0 and it's been slowly going up. We're at 2 volts per division and we're at 0.5 millisecond sweep time, so we're at 2,468 volts now output on this full bridge rectifier, and it's slowly going up. Okay, so here's the waveform with the light off. So we're just at around 8 volts there, and you can see the negative spikes with the positive spikes as well. Alright, so we're slowly growing. We're currently at like 11 volts, and you can see that noise. So what I'm going to do is I'm going to take a 50 volt 100 microfarad regular electrolytic capacitor, and I'm going to touch it on the full bridge rectifier here. The flash of the LEDs, I kind of missed it. But you see the noise there on the little peaks are gone. Now, to prove this is real energy going through here, I'm going to try to take a video of this little flash here. Prop my phone up. So I got a wire. So I'll connect it to the ground side, and I'll arc to the positive. Alright, so you saw that flash. And so basically, just an interesting effect. We are very, very slowly growing, it seems, in voltage across this full bridge rectifier, which is kind of interesting. So now that this is discharged, let's try to see if I can capture that LED pulse back there of those infrared lights. So I kind of see a flash when I touch it to this. I don't know if you saw that, but kind of interesting. And I just touched this briefly for a moment, so let's see how much energy it gets. So once again, I'll touch this to the ground and then touch this positive. And that just touched it for literally less than a second. That's pretty amazing, right? So yeah, this has a lot of potential, I think. I wonder if it stays that many volts if I were to turn it off. Still holding that electrostatic potential there. Kind of cool. But you don't see those pulses, obviously. All right, so let's stop that. So I wonder how many times I can just like keep sipping off this. So let's look at these LEDs again. So I'm going to tap this, right? See a flash? Now check this out. I'm just going to do it a few times just to see, just for the fun of it, just to show you guys. Okay. Boom! So what is this? So this is my quantum vacuum pump that I just charged up with my Bendini motor. And I charged this battery up with solar power to serve as a trigger input energy for this motor to essentially get the right pulses for this to serve as a vacuum pump. And kind of looks like a mess right now, but I'll do a more thorough video explaining. And yeah, here's the electrostatic potential still holding. And so once you build it up, you know, because it keeps ringing, and we're not killing the dipole here, right? So this thing just keeps ringing. If I were to measure this, you'll see that waveform. It's like a multi-wave, it looks like multi-stranded DNA almost, like helical structure. Really, each side is being fed off of these 88 turns of number 20 wire, and takes up this amount of width. And it's same on the other side. And you can see I biased this with diodes, and that goes into these graphene supercapacitor that are double wall, 35 volt, 10,000 microfarad. And the LED is just an indicator. This is on, these will be off, and then when these are on, this is off. Kind of interesting, even though they share a common in parallel wiring. As you can see, this neon bulb is just taking a beating. I need to change it out. I already fried a couple. So I need higher voltage stuff, it seems, to get this to work nice and proper. And what's interesting is this neon bulb is not flashing at all, but it seems to be getting some like deposits on it, it's like darkening. It's hard to see. So I got a small helical coil right here that wraps around, and basically that's coming off of a one wire right here that's going sandwiched in between this U-shape and U-shape iron core. And so that one wire splits, right? And it goes this little cap bank. So I have a really small ceramic capacitor as well as these two capacitors that are larger. And that goes into this crystal uh, quartz wrap. And then the output of that is like in series with this. And then I have a diode, blocking diode, to force it basically into this primary coil as like an additional pump, as like an amplification. Same with this like graphene supercapacitor. I don't have that set up on this side. This is just going to the LEDs. But the idea is I could do this on both sides, and this is like surge overflow to amplify energy into the vacuum pump primary coil. Um, and basically, this is creating an avalanche effect, like I'm regulating the Bendini motor output with this electrolytic capacitor in series instead of in parallel. I tried both with this neon bulb, and when it's in parallel, essentially it flashes in sync with these neon bulbs. But this kind of creates a phase delay effect and controlled electron flow a little bit with the avalanche effect. And this electrolytic capacitor, if I were to spin it around, is 1 microfarad, 100 volts. So the idea is, you know, I want to make sure I pulse it with high enough frequency to keep myself safe and everything. And then if I were to stick my finger in the water, you don't see it, but if I were to be able to zoom into that noise right there, you'd actually see the waveform be altered by my finger. You can only see it when it's at 0 to where I can zoom in with the millivolts. So I've been experimenting for a few days, and you know, this will be like over 90 volts because of the neon bulb, but it's cold electricity, and you know, it doesn't shock you. When I measure it with the multimeter, it barely goes up at all. But like I know it's working because like I'll measure this if I can at least. So here's negative, here's positive, and you can see the voltage here. Wow, 50 volt DC meter. So look at the middle line between the 10 and the 20. So we're close to like 14 volts. I've noticed in certain configurations, you know, I touch this knob and the amplitude goes way up. I touch this and it goes down. In other configurations, I touch this and the amplitude goes up. Or I touch this and the amplitude goes up. Let's just see if this is like still going after all this time of talking, you know. So let's just tap this. I haven't tapped this yet, but let's just do a quick tap. Boom. And let's see how much energy that captured. Prop my phone up here again. Okay, so I got my wire. Always use your right hand. And then I'd like to do the ground first and then snap the positive. And let's go. Oh, it welded. Nah. There we go, I got it off. But let's snap this supercapacitor. See if that goes down. And let's go to 50 volts just to be safe for now. Oh. Well, I think I accidentally just discharged it by getting the wire caught and pulling it out there. Oh, so clearly it charges up. Okay, now we're back down to 0 state. Okay. So yeah, that was after it already discharged on accident by pulling this out. It got caught on this little lead here. Okay, so as you can see, we are now centered on 0 again. So let's zoom in now. So that's 10 millivolts. So it sees like 15 millivolts or so of electrostatic bias, even though it's off. And if I were to stick my finger in, that's me sticking my finger in the water here. So Yeah, that's on the ground side of the AC. It's not even on the positive side connected to anything on this full bridge yet, see? Okay, so now I'll connect the positive side to the end of this, which is the negative terminal of this primary. All right, I got it connected, as you can see, and this went off of the screen. So I got to go up to 0.2 millivolts, or no, just 0.2 volts per division. So it's like at 0.3 volts or so. Wait, 0.1, 0.2, 0.3, 0.4? I don't know, and somewhere between like 0.2 and 0.4. But the point is, it hasn't been turned on. All I've done is just connected this positive here. And now I'll just shove my finger in. So now my finger is in the negative side and we don't see anything. I'll touch the lead. We don't see anything. So basically we only see that signal when the positive side is free. Okay, so now let's turn on the Bendini motor. See that little flicker? Just hand spin it, get it going. See all these pulses. See it rise. Kind of fun. So we're charging this graphene supercapacitor. Go to 0.5 volts per division. So if you had an array of supercapacitors and even like a mesh array of like inductors, bridging capacitors that are basically like if you had a line of capacitors and then another line of capacitors, and then each node you would like bridge with an inductor, and you can make like the sizes of the inductor like go from like small to big or big to small, but essentially you know, maybe we could capture more energy. Oh, we just hit a different harmonic at 1, 2, 3, 4 volts or so. So I'll go to 0.2 volts per division. So let's just turn this off. So the positive energy can't come out of this way, but it can come out of this way, which then can loop through to the positive side here. And so the idea is this keeps ringing if you don't discharge this. And so you could take some energy off of this if you want to, off of this ringing, and maybe put it to a battery bank through capacitor like this. Then maybe you could have multiple of those, like from over there even, and yeah, maybe even multiple of these coils here with multiple capacitors and water capacitors, which could go to multiple batteries, and those batteries could be all wired in parallel. And then a small amount of input energy could potentially, you know, power a decent amount of loads. Let's see those 2 volts.